and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. In our previous lesson, we discussed the dual nature of matter. In today's lesson, we will discuss atoms and nuclei. They are the building blocks of all matter on the planet. This is an exciting subject, so let us begin. It is amazing to think of something as small as an atom in real life. It is impossible to truly identify the size of an atom, but they're approximately 2 picometers long. A picometer is 1 trillionth of the length of a meter. This is the smallest unit of measurement that we use for length. Exact measurements are impossible because the outer edge of an atom has a cloud-like composition of electrons, so they are measured by atomic radius. Atomic radius is the distance from the center of the atom to the furthest electron ring. Before the 20th century, there had been many models of the atom. Between 1909 and 1911, a man who is often called the father of nuclear physics, Lord Ernest Rutherford, introduced a new model named the Rutherford model. He conducted an experiment with his students and made a very interesting discovery. This is a demonstration of Rutherford's gold foil experiment. The goal was to prove that charged particles in a vacuum would pass through the foil and deviate slightly from a straight line as they ran into electrons. This was the case with some particles, but other particles were deflected at much larger angles than expected, even in some cases returning along the same path. This contradicted the Thomson model, which was the dominant theory at the time. Rutherford conducted the experiment many times and decided that the particles must be bouncing off a much larger body than electrons, and that a mass with a charge big enough to bounce these particles must exist in the center of the atom. Rutherford named this body the nucleus. The nucleus has become critical to all our studies of atomic physics. Rutherford's model of the atom is shown here. Almost all the mass and the entire positive charge is concentrated on the central nucleus. Most of the atom is empty space, and electrons orbit the outer edge. While Rutherford's discovery was a major breakthrough, there was still much to investigate in regards to the specific energy structure of an atom. The missing component in Rutherford's theory was that it had no way to explain why electrons did not spiral inward, making the atom unstable. In 1913, Niels Bohr introduced the Bohr model of the atom. Bohr's suggestion was that specific energy levels exist within an atom's structure, and that electrons orbit the nucleus along rings, in the way that planets orbit the sun in our solar system. His theory explained that electrons in a lower energy state would orbit further away, while the electrons with a higher energy state would orbit much closer to the nucleus. It is possible for the electrons in an atom to exist in different states, but it is important to note that electrons can only exist at specific energy states, meaning we will not find electrons with energy between the rings. The Bohr model demonstrated that electrons have fixed, specific orbits. Before we continue, let us do a quick activity to review the two models. What was Rutherford's most important discovery? What was Bohr's most important discovery?
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. If you have been following along up until this point, this should have been easy for you. For Rutherford, the most important discovery was the nucleus. The nucleus is the foundation of nuclear physics today. Bohr's most important discovery was of the stable orbit of electrons along fixed rings in an atom. If these match your answers, great job. As we mentioned before, the electrons orbiting the nucleus all have specific energy states and travel along rings or shells at specific energy levels. Each ring can only contain a specific number of electrons within its radii. It is also possible for these electrons to move between rings. An increase in energy will cause an electron to move from a closer ring to a further ring, and a decrease causes electrons to move closer. However, they will only gain or lose energy at the moment they transfer from one ring to the other. The amount of absorption or emission of electromagnetic radiation needed for an electron to change rings is determined by an equation called the Planck relation, which states a change in variable energy is equal to the higher energy level minus the lower energy level. It is expressed as you see it here. Students, let us review the lesson with an activity. For each question, find the appropriate answer.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Let us go through the answers together. The first question relates to the use of Planck's equation. We must simply calculate the difference in energy level by subtracting the smaller energy value from the higher energy value. Thus, the answer is 2 times 10 to the power of -2. The Rutherford experiment concluded that an atom must be composed of a larger central body that is orbited by electrons. If your answers match the ones shown here, great work. Students, you are well on your way of understanding the basis of atomic physics. Understanding the history of the Rutherford and Bohr models of the atom, as well as the behavior of electrons around the nucleus, are key concepts that will be applied throughout this unit. I hope you have found this informative. Until next time, thank you, teacher. Thank you, students.